Alrighty, we'll go ahead and get started in just a minute here. Thank you everyone for joining. Just a couple logistics before we do get started. There is a Q&A feature attached to the webinar, so feel free to chat any of your questions. I have a colleague who's monitoring all those questions. He'll be sure to chat you back and answer. You can also pick up some of the answers at the end if there's anything I feel like we didn't get to, or the whole group should know. Also, if you do have the option, the best view for viewing the webinar is the side-by-side mode. I do have quite a few cool metal parts with me here today that I'm going to be showing off. I also have an overhead scope here to show you some parts in detail. So it's best to have that side-by-side view or be looking out at least for the camera to see both the slides as well as the camera and the parts I have with me here today. We'll go ahead and get started in just a minute. Alrighty, let's go ahead and get started. So today, as you probably know, we're going to be talking about 3DP for machine design. Specifically, we'll be talking about the desktop metal products. A little bit of the agenda today. We'll start by talking a little bit about what some of the challenges are in the machine design industry and how metal 3D printing actually alleviates some of those challenges. We'll talk a little bit about what the promise of 3D printing is and specifically how those apply to machine design. Then we'll look at how these three different systems work and a bunch of application examples. We'll talk about Fiber, which is the composite printer, Studio and Shop, which are both metal printers. And then we'll look at some case studies of some real life desktop metal customers, how they're using our products, how they're adding value in their industry. So what are some of the challenges that we're seeing in machine design today? One of these challenges that we're almost always hearing is in terms of low volume production. When you're producing parts in low volume, these inexpensive mass production methods like casting, metal injection molding, forging, stamping, plastic injection molding, they're just not possible because they require hard tooling. That means that, for any part that's being produced in lower volume, usually like less than 100 or so, 1,000 parts, the costs are quite high. The lead times are generally quite high as well. And, with machine design, there's often quite a few custom components required that are being produced in low volume. So this is a huge challenge we're seeing in machine design. The need to test, iterate on multiple complex geometries in parallel, especially when we're working in metal. If you want to be able to prototype, functionally prototype, do some design iterations to make sure you're producing the best part, this is a challenge, because of these lead times, of these, high costs in parts, that it can be very expensive to iterate on parts, specifically when you want to do it in parallel. Managing a complex bill of materials and assembly procedures. A lot of these machines that we're seeing are thousands, if not tens of thousands, millions of parts even. So managing these very, very, very complex and challenging bill of materials and assembly procedures to ensure that everything's being put together correctly and that we're warehousing and inventorying everything we need. CNC shop bottlenecks, foundry lead times, and NRE, non-recurring engineering costs is something that we see a lot of in machine design. As we're designing our machine, we're going to need many different CNC parts. We may need to outsource some stuff to a foundry. The lead times are very high generally on these foundries, as well as, with many CNCs that are getting very, very, very backlogged. So this is a challenge that we have to navigate around, as well as these non-recurring engineering costs where we may have to invest in some fixturing or, some programming to CNC a single part, where these costs are, they're non-recurring, but since we're producing in low volume, they really add up. They really add to our part costs. And then, of course, our fabrication of aftermarket replacement parts. If a part were to break on our machine and they need a new one, does the tooling still exist to make that part? Do we still have the foundry available that made that part in the first place? How do we replace this part quickly and affordably for our customer? So how does additive manufacturing help with these challenges? In terms of low volume production, of course, there's no tooling involved at any point during the 3D printing process. This means that a part cost is going to stay the same whether you need one of those parts or you need 10,000 of those parts. This means that, when you design your part, you quote your part, the cost is going to stay the same. You don't have to factor in tooling. You don't have to factor in all this NRE costs on your part. The part cost is going to stay the same. This means that low volume production is very easy because, simply pull the file, throw it on the printer, and in a few days, I have my finished part in my hands. We can now rapidly prototype metal parts in the comfort of your office. This means that now we're able to quickly and affordably create complex metal parts that you can now test under, high loading, heat and corrosion resistance. We're not just testing form and fit like we so often see with plastic 3D printing, but now we're actually able to test the geometry, to put our gear into our machine and see how it performs. In terms of managing these complex bill of materials and assembly procedures, it's very common to be able to do assembly consolidation. It's not uncommon to see in the industry people doing assembly consolidations of 100 to 1, 50 parts to 1, where, the only reason that assembly existed in the first place was because it was cheaper and easier to manufacture all those parts separately and assemble them. This leads to these very complex bill of materials, these assembly plans, but now that we have this additive method, it's very common to be able to consolidate many of these assemblies into one simple part. In terms of CNC bottlenecks, really with 3D printing, especially with the studio system, which is the printer behind me, we're now able to take manufacturing into our own hands. We can decide what's queuing. This printer is going to be a workhorse that's going to run over the weekend. It's going to run all night long. No operator burden. Simply put your parts on. In a few days, you're ready to go. This is going to take a lot of stress off of our machine shop and really allow us to take manufacturing into our own hands. In terms of aftermarket parts, of course, there's no need now to warehouse replacement parts. The system's so fast, it's so affordable. The part cost is going to stay the same if you make it today or if I make it in 5 years from now on the same printer. Just pull the file, throw it on the printer, ship it out to your customer in just a few days. So let's talk a little bit about the promise of 3D printing. We just talked about a lot of these, when we're looking at the solutions, but like I just mentioned, rapid prototyping. And the big thing with rapid prototyping with desktop metal products is that it's not just form and fit anymore. I'm not just putting my plastic part into the machine to see if it fits, but now I'm actually putting it under high loading, high heat, corrosion environments to make sure it's really the optimized geometry. Part consolidation, we'll look at some of these parts later, but the ability to combine multiple of these assemblies that were only designed that way because they were designed for traditional manufacturing into one simple part, simplifying bill of materials, reducing part costs, and just leading to a better, more optimized component. Complex geometries. This is one that I like to explain a little bit more in depth, but the idea of complex geometries is not new. People have been creating complex geometries with traditional manufacturing for a long time. But I kind of like to say justifiable complex geometries. Because with 3D printing, since it is an additive method, we can now create these very, very, very complex geometries, incorporating these lightweighting features or different features that would be very expensive to produce with traditional manufacturing, but aren't significantly adding to your part costs with metal 3D printing. So now we can create these very complex geometries that we may have wished to have done before, but it was just too expensive, too costly, too difficult that we couldn't justify it. But with 3D printing, we're seeing tons of parts now that people have wanted to produce for a long time, but they could never justify it before. With this system, you're going to be able to justify these very complex geometries. Design customizations. Of course, since there's no tooling involved at any point during the process, you can be changing your part on demand. I can print this today, and then tonight I could throw this on the printer and have this in the morning. So this allows us to, design our parts specifically for our customer. If I have one customer who needs a little bit of a tweak, no problem. Just adjust my CAD file, upload it to the printer. A few days, I'm ready to ship out that part. On the other side of it is the idea of actually doing rapid tooling. So, tooling is generally some of the most expensive and longest lead time components to get. That means that, if this is what we were talking about earlier with the issue with low volume production. If I am going to have a part stamped, if I am going to have a part injection molded, it's going to take a long time for me to get those tools created. But with printing, we're able to print these parts very quickly, especially these tooling components out of some of those more difficult to work with steels like an H13 or a 4140 steel, where I can now print this part in just a few days. I can touch up any critical dimensions on a CNC or an EDM machine. And, now we're ready to use that tooling component, actually to manufacture some other end-use parts. On-demand manufacturing, like we talked about a little bit, this ability to simply, no longer needing to warehouse all of these components. I can simply just pull the file, load it on the printer, ready to ship it out in just a couple of days. This last point is going to take a little bit longer to come around, but the idea of really re-engineering the supply chain. So many parts are made all over the world and then shipped on these large, cargo tankers to different locations, simply because it's cheaper to do it that way than it would to be to manufacture it on site, in the US or in Europe, depending on, or, even in Asia, depending on where you are. But, as we're seeing, more and more of these printers being deployed around the world and the part cost is staying the same no matter where these printers are deployed, we're seeing this, kind of re-engineering of the supply chain where people are starting to send digital files rather than end-use goods. Like I said, this one's going to take some time to come about, but as we're seeing more and more printers being deployed, we're seeing large companies that have offices all over the world. Rather than having to ship them parts, they just send them the file and they print it on their printer on location. So a little bit about Desktop Metal. The original challenge that we saw when founding Desktop Metal was we wanted to generate this office-friendly 3D printing technology. We wanted it to be on demand. We didn't want there to be any special facilities or operators required during the process. At the same time, we wanted to give people a broad palette of familiar materials that they are already used to working with, that they've used in the past. And at the same time, we wanted to give engineers and designers a path to mass production. We didn't want 3D printing to stop just at the prototyping design stage, the low volume stage. We wanted to move to that mass production to actually make 3D printing viable for those higher volumes. So that's really how DM was founded. And DM was founded with the goal to make 3D printing accessible for engineers and manufacturers. And what I want you to take away from this mission statement is this idea of accessibility. Metal 3D printing has been around for 20 plus years now, but it really hasn't been accessible to anybody but the very, very, very high tier, high-end manufacturers for aerospace, medical device, etc. Desktop Metal really wanted to make this technology accessible to the everyday manufacturer, to the everyday engineer, to the everyday student, to make, really put this amazing tool to be able to create these complex metal parts in the hands of the everyday engineer, not just these high-end, luxury, almost luxury parts that can really afford those very expensive machines and those very expensive part costs. So looking at our product line, we have our fiber printer. We'll be talking about that today. That's for continuous carbon fiber parts, printing PEEK and PEC, nylon, fiberglass. Creates really, really strong parts with excellent surface finish. We'll look at a lot of these today. Then you have the studio system. That's really the printer that I have behind me. That's great for your office-friendly production of metal prototypes, one-off parts. I have a bunch of them with me here today. Again, we'll look at tons of examples. We'll talk about how each of these different systems work in a little bit. We have the shop system. That's a binder jetting machine that allows you to print these fully dense, very, very quickly, high volume parts featuring, very, very, very fine features. We'll look at a lot of these in detail as well, but that's really, ramping up the volume. When you want to go from maybe 10 parts a week to hundreds or thousands of parts a week, you can move from the studio system up to the shop system. And then on the very, very, very high end, we have the production system, which is used for really, really unlocking the mass production of metal parts. We're producing hundreds of thousands of parts per week, millions of parts a month or a year, really, really unlocking high volume, low cost per part, allowing you to actually go to end use components with that system. We've been shipping, around the world for a few years now. We have partners in 49 countries. So wherever you're watching today, there's a system nearby. And, we're working with some of the largest companies in the world. But what I also want to point out is we're also working with some of the smaller companies, the mom and pop machine shops, the 1 or 2 man design agency, the small machine shop. These systems are so accessible. We're adding values to the companies that are like Toyota, as well as the tiny little companies that are buying their first 3D printer. These printers are accessible. They're unlocking the price point. They're unlocking the potential for everyone to get their hands on this technology. So that's just something I want you to take away from here too, as well as you probably see some big names on this slide, but it's not just exclusive to those customers. We're really embracing technology, adding value across the board. So specific to machine design, I hope you recognize some of these names. We'll look at some of these companies today and how they're using this technology, but a lot of the big players in machine design are making excellent use. Companies like Makine and Lockheed Martin are making excellent use of their Desktop Metal systems today. And we're really seeing machine design parts, across a variety of applications. We'll talk through a lot of these parts, but, bearing housings, different gear assemblies, roller screws for linear actuators, different housings to mount different motors or different flanges and bearings, axle components that are made out of strong continuous fiber for lightweighting reasons, different custom gears, as well as, as I mentioned, motor housings for holding stepper motors or servo motors are excellent things to print on the fiber print. So let's start with fiber. Like I mentioned before, fiber is our carbon fiber printer. It's printing carbon fiber, fiberglass, PEEK, PEC, nylons as well. And let's talk first about how it works. So, as I mentioned before, fiber, we commonly like to say, stronger than steel, lighter than aluminum, printed at your desktop. And I'm going to justify this statement to you over the next couple of slides, and you'll understand what I mean. But fiber really allows you to create these incredibly strong parts in a wide range of different materials, and we're making it super accessible to everyone. It's very easy to use. It's coming at a price point that makes this technology available for almost everyone. We have tons of universities buying. We even have personal users buying this machine. So it's very, very, very accessible in terms of cost as well as ease of use. So quickly, how does this printer actually work? This printer actually features two different print heads. One of these print heads is going to be your traditional, 3D printing nozzle. It's got a 0.4 millimeter diameter. It's extruding just a filament through it, and it's going to lay down, kind of this chopped fiber. So it's not a continuous fiber that you think of when you think of these long strands of carbon fiber. It's just little chopped up bits of that. That's going to be mixed with a nylon or a PEEK or a PEC, and it's going to increase the material properties a bit, but nowhere near what you get out of continuous. So what you're looking at on the screen here on the right, that's a layer. You can see all of what's in gray or orange. That's all being printed by this nozzle out of this chopped fiber. Then we have this second print head. This print head is going to be printing this UFP tape, which is micro automated fiber placement. That's going to be printing these 3 millimeter wide strips of continuous fiber tape. So what we're going to do is we're kind of going to print our shell with our nozzle, which is that first print head, and then we're going to reinforce it with these tapes that we're laying into the part. You can almost think of it as rebar in concrete, if you're familiar with that. Concrete's going to be your chopped fiber, then your rebar is going to be your super, super strong reinforcement carbon fiber to reinforce that part. So everything you're seeing here in purple are those strips of carbon fiber tape that are each 3 millimeters wide. So, we can print lots of detail with our high resolution nozzle, and then we can lay in these strips of tape to really, really reinforce the strength of this part. So, for example, on this part here, this is a yoke similar to the part that I have with me here, that I have right here, but everything that's kind of ghosted out on this part is going to be printed with that first print head in that FFF filament, and then everything that is, actually those gray slabs would all be printed with that continuous fiber, carbon fiber. So these tapes are made out of these multi-directional fibers that are running constantly throughout the part. There are these wide tapes that we then slit into slits. But these are going to give you an incredible strength. And by altering the direction of these parts, you're going to get a very uniformly strong part that's going to have incredible material properties. So let me now justify to you, how we said stronger than steel, lighter than aluminum. What you're seeing in purple here on the left, those are the material properties of that filament I talked about. That's what's being printed with that FDM nozzle. So if you're looking at the tensile strength of, PEEK and carbon fiber, we're still at about 100, which compared to ABS on the right, which is at 39, still pretty great material. If you're looking at the densities, we're about 1.17 to 1.38. So still very, very low density, but very, very, very strong material for an FDM material. Then we look at the tapes in red here. Those are those continuous fiber strands of tape that were being laid down with the second print head. Those have material properties of 1,400 to 2,400 megapascals in tensile. Steel, for example, 4140 steel is about 655. So we're getting almost 4 times the strength in tensile for these continuous fiber tapes than what you do with a 4140 steel. So there's my stronger than steel. If you look at the, the density of aluminum, 2.7. All of our tapes and FDM filaments are, almost half of that, about 1.45 to 1.57. So that's where we're getting our lighter than aluminum. So these materials in combination, you can create these incredibly strong parts that are incredibly light. Of course, you need to worry about your fiber direction a little bit. Be thinking about how am I going to align my tapes into the correct loading to ensure that they're in tension, but we're getting this incredible strength out of these materials. So let's talk through some applications, look at some parts that are making use of this. Specific to machine design, tons of custom brackets. You can imagine, I have a bearing, I have a motor, I have some sensors I need to hook up to my machine. I was able to print each of the brackets that you're seeing on the screen here in less than 1 hour. You can think about, these parts are incredibly strong, they're incredibly light, and they're incredibly affordable while being able to be produced in less than 1 hour. You can think about how beneficial that technology is to be able to, oh, we need to rig up a sensor into our machine real quick. No problem. Let me model up a bracket, throw it on the printer. I'll come back from lunch, pull it off, and we're ready to install it. Great application for the fiber printer. This is a specific, motor housing. I have it here. This is actually used for a BattleBot, which is a fighting robot. This is used to hold the electric motor in place. This part was printed out of PEEK, and so because during the competition, these parts are exposed to some high heat, high corrosion environments, even flamethrowers, things of that nature. So the PEEK is going to give this part that excellent resistance to temperature, and it's also going to hold this motor firmly in place. This part was able to be printed in about 10 hours. It's a little bit larger, but think about it, I could print this overnight, and it cost about $64 because it was printed out of PEEK. Balance shaft gears, part you're seeing here, these parts are used to reduce vibrations in rotating parts due to unbalanced dynamic forces. Generally, they can be machined out of steel, but we needed a part that was lighter for this application. Lightweighting was key, so we were able to print our gear. This part is very, very light. It's only 79 grams. Cost about $67, and again, can be printed in about 10 hours, printed overnight, ready for it to have it in my hands the next morning. This is a lever connector for a wheelchair. This part is actually used to it connects the levers to the actual axle drive, where the chain is to the wheels on the actual wheelchair. Of course, with a user-powered device like a wheelchair, weight reduction is critical. So these parts were originally being machined out of aluminum. It required quite a few weeks of lead time, and the parts were still quite heavy. But by going to this composite part, we were able to greatly reduce the mass of this component. We got this, we still have a very, very strong part. This was printed out of nylon mixed with a fiberglass, and a cost of just about $12.67. Again, 12-hour print time, printed it overnight, ready to install it on the wheelchair the next day for this extremely light, strong part. So now I'm going to move over to metal and talk a little bit about the Studio System. The Studio System is the machine that I have behind me. You can see the printer and the furnace behind me, but it's really this office-friendly metal 3D printer. Before I get into how the Studio System works, let me first briefly talk about metal injection molding. Metal injection molding is a powdered metal process. It enables you to create these very, very, very complex shapes and then mass produce them utilizing these inexpensive metal powders. It's similar to the plastic injection molding process. We're going to inject these powders into a mold. We're going to eject it out, and the parts go into a furnace. I'll review the process in a minute. Important to know, these parts are being used across a wide variety of industries, from everything to aerospace to consumer products, even medical, firearm, etc. They have widely accepted validated standards, ASTM and ISO standards, creates excellent parts. The problem with this technology is really the process. It really can only be utilized for these very, very, very high-end components, high-volume components, excuse me. So looking at the top section of this slide, we start with this metal powder, this metal injection molding powder that I mentioned, this low-cost powder. We're going to mix it with a feedstock, which is a binder, mix it with a binder to create a feedstock. That binder is similar to a glue. We're then going to inject that into a mold. That's going to form the shape of our part, similar to a plastic injection molding process. We're going to eject that out of the mold. So then we're just going to have our part that's made out of just binder and metal powder. It's only being held together with the binder. If you dropped it, it would break. But then we're going to put it into a debinder. That's going to remove most of the binder material out of that part. Then you're going to go into the furnace. The furnace is going to get just below the melting temperature of the material. It's going to remove the last bit of binder holding the part together, and you're going to sinter your part into a strong, dense metal part. So again, great technology, allows you to create lots of these, high quality, small parts very, very quickly in very, very high volumes. The issue in this step is the tooling, of course. You need this massive injection molding press that wouldn't even fit in the room that I'm in right now. You need these strong steel detailed molds for each different part you want to make. So if you want to make changes to your part, you're going to need a different mold. If I want to make a different part, I'm going to have to wait weeks for those molds to come through. So it's very, very inaccessible unless you're producing in high volumes. So the Studio System kind of leverages that same technology, but removes a lot of the issues in terms of accessibility. So the feedstock, rather than creating this loose powder feedstock, that's kind of dangerous. You have to be careful with powder handling, wear a respirator, etc. We now create a feedstock in the form of a rod. That rod is fully encased in a wax to ensure that you're never exposed to any metal powder throughout the process. I wish I could pull one out of this printer here and show it to you. It's a very, very, very safe rod. You're never going to be exposed to any powder during the process. Rather than injecting that rod into a mold, we're simply going to print that rod layer by layer. This means that there's no tooling involved at any point during the process. So, for example, I could print this gear, tonight, and then, when it's done in the morning, I could throw on, this little connecting bar I have here. This will be done, in the evening, and I could throw on the worm gear overnight. I can constantly be printing different parts because there's no tooling involved. You're then going to put the parts into a similar debinder. It's going to remove that binder material, most of the binder material. Then you're going to go into the furnace. The furnace is going to sinter your part into a strong, dense metal part like I have here with me today, and you're going to be ready to go. So quickly, a little bit about 3 pieces of equipment. I have just the printer and the furnace behind me, but the printer is similar to the safest and most widely used 3D printing process of FDM, where we're just printing parts layer by layer. This means that they have, familiar design guidelines that, you're already used to designing for. You have these office safe materials, so there's no powder handling at any point during the process. Debinder, again, targeting accessibility. It's got slow emission design, automatic fluid distillation and recycling. It's safe for your office environment. The parts go into the debinder dry, they come out of the debinder dry, so you're never exposed to any, debind fluid throughout the entire process. And then the furnace, again, first office-friendly sintering furnace. It's going to fit through your office doorway. There's no residual stresses involved in the process because we're going to heat up and cool down uniformly. It's got a peak temperature of 1400 degrees Celsius, which allows us to sinter, a wide variety of alloys to the highest material properties possible. So what is the result of this process? We're getting what we call a near net shaped part. Parts with resolution, accuracy, surface finish that's similar to what we would consider compared to a high quality casting. Let me switch over to my overhead camera now, and you should be able to see, one of these parts in a little bit more detail here. Dimensional capabilities are about plus or minus 0.8%, but it's important to know these parts are fully compatible with traditional post-processing, processes. For example, this gear here, I printed this part, I debound this part, I sintered the part, but I need a little bit tighter tolerance than 0.8% on this inner diameter. So what did I do? I threw it onto the lathe. I just machined off, just a millimeter off this just to achieve that, critical dimension. That's going to save me a ton of time compared to machining this entire gear out of a wrought block of 17.4. So, huge time savings there. As well, these parts are fully compatible with traditional finishing operations like tumbling, media blasting, plating, welding, heat treatment. So, whatever finish, whatever properties you need, you can get that with the system. It just may require a little bit of post-processing. Important to know, these parts are fully functional coming out of the furnace. Many of our users simply use the parts that way, that that the tolerances are more than fine, the finishes are more than fine coming out of the furnace, so the parts are just, are fully usable coming out of the furnace. So looking at materials, a wide variety of, familiar materials. We have 17.4 pH, a very common stainless steel. It has excellent mechanical properties. 316L, another common stainless steel, a little bit better at high temperatures as well as under some specific corrosion environments. Alloy 625, also known as Inconel, nickel-based super alloy, excellent at very high temperatures as well as some specific corrosion environments. H13, that's a tool steel, excellent hot hardness. It's great for constantly fluctuating temperatures as well as some specific, which makes it great for injection molding cores, which are constantly being heated and cooled. 4140, another common low alloy steel, has excellent hardness values, makes it great for end effectors as well as for some sheet metal tooling, housings, etc. And then of course copper, you have your high purity copper, which is excellent for those thermal and electrical conductivity applications. So quick recap on the studio system. It's really this office-friendly metal 3D printer. No hazardous powders at any point during the process. There's no respirator involved at any point during the process. There's no dangerous lasers involved like, traditional powder bed fusion processes or traditional metal 3D printers. You don't need any of this third-party equipment. We're going to provide everything you need to print the part. Of course, there's no dedicated operator involved. Simply upload your part. It's going to print overnight. You're going to move it to the debinder, less than 30 minutes for the entire, part process. There's no welded supports. Your parts are going to come right off of their supports because we have an interface layer involved. to ensure they don't sinter together. And then no special facilities. This system is very easy to install into into your office environment, into anywhere you need it to go, making it super, super, super accessible. So let's talk through some applications. Motor mount, part that I have with me here today. In machine design, you're constantly using lots of different motors. So for example, this is a motor mount that's used for mounting a NEMA motor. The geometry machinist would require several different CNC setups to be machined. So during the prototyping and low volume stages, this part can be very, very economically produced when we're producing it in lower volumes. So for example, each one of these is going to cost me about $56. The traditional machining cost on this part was over $245. So right there, we're getting about a 75% cost savings on this part. Custom mechanical couplings. I'll flip back to my overhead camera so you can see some of the detail on this part, but these are custom mechanical couplings that are used to transfer power between two rotating pieces of machinery. There's quite some complex geometry involved in these parts, from the teeth and as well as the male and female of these two components. They need to be metal for the stiffness. These were actually able to be prototyped on the studio system in just a couple of days, but then they're actually able to move to the shop system in binder jetting to produce these in mass production, which was an excellent application. Roller screw, another part that I have with me here today. This is used in a linear actuator to open and close the pilot valve in a steam power plant. Traditionally, this part was manufactured out of 7 different components. The gears were manufactured separately. The roller was manufactured separately. There was some assembly involved. Of course, this part's under very high loading because of there's a lot of high forces involved in opening and closing this power plant valve. So 17.4 was an excellent material choice for this part. Just it has some mild corrosion resistance as well. This part was able to be produced for just $86. The traditional machining cost was about $1,900 on this part. So a great example of how we can save a lot of time and money by producing this part on the studio system. You can see here, that original design, the gears were separate, as well as there were some set screws, but now you can print the entire part as just one component. Some worm gear components. So you can see, there's a couple different parts that we are able to print from this worm gear speed reducer. That front motor mounting flange. When we're prototyping that part's eventually going to be cast in higher volumes, and then have some secondary machining done to it. But before we do that, it's very beneficial to prototype that part for different motor sizes, to get the geometry right, to get a geometry that we're happy with. Rather than having to go to a foundry or pay very, very expensive machining costs, we can simply throw it on our printer, produce that part in a couple of days at a very affordable and at a great lead time. Specifically, this worm gear, this is a very common component in I'm sure if we have the machine designers on the line today, you'll recognize this component. One of my favorite mechanical components, but used when you need a gear reduction in confined space. Metal 3D printing, we were able to prototype this part very, very quickly and affordably. So if we want to be able to iterate on different teeth profiles, different pitches, different thread sizes. Super, super easy just to print these rather than having to spin up a thread cutting machine or to do some very, very expensive machining operations. This part was produced in 4140 for that excellent hardness value, produced for just about $86 on the studio system. Traditional cost for machining was about $390, so we saw about a 78% cost savings on this component here. Very, very fun part, I think. Heat exchanger with conformal cooling channels. So I have, this is another one I have with me here today. This part's just a little bit oxidized. I haven't brushed it in a little while, but it's that high quality copper. Here we're able to incorporate, those conformal cooling channels that are actually wrapping through this part. You can see them being printed, layer by layer, then building up into this component. Sorry. So this is used for cooling in a chemical plant operation, but copper is going to give us that excellent thermal conductivity. While we're able to incorporate that helix that's winding through the part to actually run some coolant through there to really increase that heat transfer rate. You can see some of the internal fins, of course, to increase the surface area as well. One project I want to talk a little bit about, it's more of an automotive application, but I think it's still very applicable to machine designers, was this project that this company Turner Motorsports did. The project that they took on was to marry this 2001 BMW M3 with a modern V8 engine. So, as you can imagine, many of the parts didn't fit together. So, what did they do? They had, one of these parts was the engine mount, which is the actual part that's going to hold this big V8 engine to the body of the car. So what did they do? They scanned up the original engine mounts. They loaded it into a generative design software. You can see here they were able to incorporate some of these keep out zones, which is the blue. So that's telling the software, do not come here, do not allow the part to go here. They're going to interfere with the car. That way they were able to actually grow this part and generate a few different examples of this component. You can see a couple of different iterations here. You can see one of them actually in the car with some Sharpie on it saying, oh, we need to make some adjustments to this component. And then you can see the final parts here where we were able to just, super optimize this component for the car. Why I think this is applicable to machine designers is you have these very complex large machines that you may need to incorporate. Oh, we got to find a way to get a motor in there. We got to find a way to get some bearings or some shafts in there. How can we incorporate generative design into that workflow? Well, we're able to incorporate these keep out zones, like I showed you, where we're telling these mounts, don't come here, and we're allowing them to organically grow. But then we throw them on our printer, and in a couple of days we have our end use extremely strong metal or composite part. This part, for example, was a little bit too large to be printed on the studio system in one component. It was outside the build volume, so we simply just, welded this part together and printed it in two parts, welded it together to create this very strong, organically cool, awesome part. You can actually see it here in the engine. As you can imagine, this engine is very heavy. These parts were printed in 17.4 stainless steel, which gave it those extra mechanical properties to make sure we were holding this engine firmly in place. Saw blades. So this is that BattleBot I mentioned earlier. Printed a couple different parts from this. One of those parts is this backstop. So this is actually a support for the BattleBot's fighting robot saw arm. It's a structural member, so it must resist lots of bending, lateral motion. Needs to be metal. It has some relatively complex geometry because they're trying to reduce the weight as much as possible. And then lead time was critical here as well. The team has only a month to build this entire robot, so they need to move very quickly. They were able to print this part for just $56. The traditional cost was, over $1,200. So they saw a huge cost savings on this component, and as well as a huge lead time savings. Another part, this is a timing belt pulley. This part actually attaches to a servo motor. It's used in a manufacturing environment. You can see the original design on the left here. That part was made out of, some aluminum extrusion, as well as, how you had two clamp collars placed on the end of it. You had a bunch of bolts as well as, some other parts. And the goal here was really to make this part less expensive to manufacture. They wanted to lighten the weight, and they also wanted to lower the inertia to allow the servos to run faster. So, they're able to redesign this part. You can see some of the lightweighting features that are incorporated into this part. You can see the coring that was able to feature into this part. They're able to reduce this entire assembly into just one component, lighten the weight to allow this servo to run even faster, actually, to improve the efficiency of this manufacturing environment. Another part I have with me here today is this pretty cool, ratcheting tool for a manufacturing environment. This tool actually attaches to, it actually goes up into the spindle and is used for tightening and loosening screws on fixturing. Of course, this part needs to be metal because it's having tons of repeated use. You can see the part here. It features this, internal gear. There's all these different ratcheting components around it. The housing is quite complex as well. Just a great example of, how we can really think outside the box. You could never justify, machining this part for what it does. It would be thousands of dollars to machine, but, we can print this for just about, a little over $100. So, a great example of, a part that is like, now we're able to justify this very complex geometry and this complex housing to, really lead to a more efficient manufacturing environment, would have lots of different moving components. A great example. So let's move on to the shop system. The shop system is really the world's first metal binder jetting system that's designed specifically for machine shops. A little bit about how binder jetting works. Binder jetting is exactly like it sounds. It jets binder. This is a powdered metal process. So you start with a powder feed box on the right. You're going to spread a thin layer of powder across the build box on the left, about 50 microns thick. Then you're going to come across with your print head array. It's going to drop binder onto that build box, onto that layer of powder, just where your part is layer by layer. So in this example, our jigsaw puzzle pieces are our actual, end use parts, but we're just going to jet binder just on those layers. After each layer is printed, we're going to lower the build box by another layer, spread another layer of powder, and the print head's going to come across again. This allows us to print entire layers of parts in just a few seconds, because that print head's going to come across very quickly, similar to what you would have in an inkjet printer, and deposit an entire layer of binder, print that entire layer. After this process is done, you're going to depowder your entire cake of parts. You're going to remove all your parts out of there. You're going to put them into a furnace, and you're going to sinter those parts similar to how you would in the studio system. First we're going to do a thermal debind here. There's no solvent debind. Remove all that binder material out. Then we're going to go up to a sintering temperature. We're going to remove that last bit of binder, and we're going to end up with these, these strong, dense metal parts. So this system is really giving you, this extremely increase in productivity. We're now able to produce, tons of various different part geometries simultaneously without the need for multiple setups, without the need for different fixturing, without the need for operator burden. If you look on the right, you can see all these different parts we're able to incorporate into one shop build. This can print overnight. They're ready to go into the furnace, in the next day. Super, super, super efficient. You can imagine asking your machinist to machine you each one of those different components. They would need, potentially weeks to do this, because of, all the different fixturing that would need to be involved, all the different programming that would need to be involved, all the different operator burden. When, it's very simple to upload all this geometries. We can set up this build in just 1 to 2 hours, and we're ready to go. An important thing to note here, it's all without tooling, of course. This is mitigating a lot of risk, mitigating a lot of cost, because we can print each one of these different parts without any tooling. So if we need to make a change to the part, simply, tweak your file, re-upload it to the printer, and we have our new parts ready to go. Lots of cool parts that I have with me here today. These binder jetting parts are really, really impressive. So first part, this little sensor housing that I have here. This part is used to hold multiple sensors in a precise location to take measurements in a running machine. So, the small features on this part make it pretty ideal for the shop system, because it's very easy for the shop system to simply just, print in all these little features that you're seeing on this part here. It also allows for a lot of manufacturing flexibility. So, if we want to, modify the design to incorporate some different sensors, all we have to do is simply, modify our CAD model, re-upload it to the printer, and we have our new sensors, hundreds of them in just a few days. The cost of this part is about $7.80 per part. We can do about 186 of them per shop build, or about 1,500 of them per week. So you can really see how that volume's increasing to print tons of different parts. This bearing housing. So this is a part that needed to be produced very, very quickly and out of steel. So this obviously holds some bearings in location to take some measurements, and they need to be produced very, very quickly. So the shop system was a great alternative, because the cost per part was just about $73 per part. Parts per build, we could do about 24 of these parts per build, and the throughput per week was about 190 of these parts per week. So really, really unlocking the potential. We can print hundreds of these, or hundreds of these parts in just about a week. No problem. Get them ready and get them installed into the machine. Another example is, you look at all these different, gears that were able to be produced, all without the need for tooling. These are parts that are used in the power transmission for an electric power drill. Of course, no tooling involved. These parts would be, hundreds of thousands of dollars of investment in tooling for metal injection molding process. But, each one of these parts can be printed, without the need for tooling, greatly simplifying and greatly reducing the cost. I really like the teeth on this part. Very, very, very high resolution. They look excellent. So let's hop over to some case studies, talk about some specific some specific customers, how they're using the system, how they're making use of the Desktop Metal products. Master Drilling. They're located down in Johannesburg, South Africa. They make these very, very, very large earth drilling machines used for drilling, miles into the ground, mostly for the mining operations, energy, oil and gas, etc. One of the parts that they unfortunately had a problem with was this sun gear. They were currently getting this sun gear from, a foundry in China with about a 3-month lead time. So when they had one of these sun gears break, they need to reproduce it very, very quickly so they could get this drill back up and running. So, they turned to the studio system. In just 3 weeks, they're able to print this part, debind the part, sinter the part. They did some post-machining operations to the part, and then did a case hardening operation as well. This greatly, of course, reduced the lead time. They went from 3 months down to just 3 weeks. It is a pretty big part, so it is a little bit longer of a processing time, as well as, they did obviously the post-machining and the case hardening operation. But, a great example of how they were able to greatly accelerate lead times for, an aftermarket component, especially a critical one where they needed to get the part very, very quickly, and this 3-month lead time was no longer acceptable. Looking at some of the results, you can see the hardness of this part as printed was about 25 Rockwell. After a heat treatment process, they were able to get all the way up to 43. It's an example of how with post-processing, you can really get the properties you need. After plasma nitriding, all the way up to 64 on the surface, of course. And, this part was successfully field tested, drilled miles into the ground for, on one of these very, very large earth drilling machines. It's a really impressive part. Ewald, they are a manufacturer of high-tech marine propellers located in Italy, founded in 1997, leading vendor of these propellers. They use a wide variety of different stainless steels for, performance, accuracy, mechanical, and corrosion resistance. So they were happy to see that Desktop Metal, had all these stainless steels they are already familiar with working with. One of the parts we're going to talk about today is this propeller pinion. This part is actually used to connect the propeller shaft to the blades, and was traditionally made out of, made with investment casting out of 17.4 stainless steel. The goal of printing this part was really to overcome the constraints that they had with investment casting. Currently, they had a minimum casting lot size of 100 pieces. If they couldn't, meet that minimum order, they had to collect other jobs. They had to wait until they could place an order of that size. Even when they did place the order, the lead time was quite long. Investment casting is a great process, but a quite complex one. There has to be alloy procurement, wax pattern setup, etc., which requires, the parts are going to take quite a long time to come back from the foundry. On top of that, there's some quite challenging labor-intensive CNC machining even after the parts come back. We have to machine the inner ribs, which is quite complex and expensive. The cutting tool also has to go deep down the inner diameter of this pinion body with limited access, which leads to, quite a difficult and challenging machining operation. So this part was able to be printed. You can see a couple different printed iterations here. You can see on the left, the one on the far left is going to be the part that was after the furnace. The one on the right is out of the off the printer. I should have mentioned there is a little bit of shrink involved in the process. About 20% happens in the furnace, but that's fully accounted for with the software that comes with the printer. It's going to scale your part for you. So really the result here was a more efficient manufacturing operation. Printing with the studio system, you can be much more responsive to customer demands. Now they don't have to, deal with this minimum lot sizing logistics anymore. They're actually producing parts much faster since they're taking manufacturing into their own hands. They can print when and where they want. They're able to lower the part cost, improve the part quality, much less labor intensive process, and they find it much more sustainable than their casting operations were. So big business impact for Ewald, this ability to produce these previously impossible geometries for improved performances. They're demonstrating feasibility of additive manufacturing in terms of, speed, flexibility, quality, and cost, and really realizing that, metal additive manufacturing is a realistic, manufacturing method for them in terms of metal. They're looking to explore, to move to some higher volumes by utilizing the shop system now. Cifarelli, also located in Italy, founded in 1967. They're a leading vendor of agriculture and gardening equipment. They have a rich history of technology and product innovation. So, of course, they're looking to incorporate, 3D printing into every, across their entire product line. The part we're going to talk about today is this shaker hook. This part vibrates over, 2,000 times per minute, has a stroke of 62 millimeters, so quite a large stroke, and is ideal for harvesting nuts and olives. So this shaker hook that you're seeing here can collect over 3,000 kilograms of olives per day with a falling rate of about 95%. So this means it's getting 95% of the fruit or nuts off the tree without damaging the tree or any of its buds. It's a very key component. The design, greatly impacts its performance, its reliability, as well as its usability. So, standard versions of this part were produced in quite high volumes, in the thousands, via an aluminum chill casting operation. But they do get some requests for these custom lower volume applications. These applications require special topology optimized geometries that are going to actually increase the strength of the part, and they have to be challenged as well because they're moving to steel, so they have some weight constraints. They can't have a hook that's any heavier than the aluminum versions because it would cause some wear on the gearboxes, wear on the rest of the part. And of course, these shaker hooks can no longer be economically produced via aluminum casting, so they're moving to steel. So what Cifarelli did was they came up with a new design, a design that was able to leverage the strength of steel, yet is no heavier than the standard aluminum part. This was achieved through some topology optimization as well as some simulation-driven design. So you can see here, they're able to load this part into a generative design software. They're able to apply some loading, some forces, that vibration of the frequency, and then allow the part to remove material where it thinks is best to really leverage the strength. Then they're able to load this part up onto the printer, print this part. You can see the green version here, printed with that U inside just to increase to ensure that it was going to adhere to the correct dimensions, which was easily removed after printing. And you can see the sintered shaker hooks ready for a field test. You can see it actually here. The result was really a part that was I'll let this go fine. So the result there was really a part that was, no heavier than the aluminum components, but much, much stronger because now it was leveraging steel. The last, customer we talked about today is Prezioso Francesco. They are a leading vendor of sheet metal cabinets for gas and water meters, on-off valves, heating systems, manifolds, etc. They service mostly the energy, civil, and industrial plant sectors. So the challenge for them is really these replacement parts for their manufacturing floor. So they're really exploring additive manufacturing to help them with their maintenance, repair, and operation parts, their MRO. They have these very, very long lead times currently. They're seeing lots of CNC machining bottlenecks when they're trying to replace these parts. And then the part mass is, they're actually seeing some reduced performance on their parts because they're quite heavy and they're looking to optimize that mass. The first part we're going to talk about is this sheet metal clamp. It's used on a punching machine. There's 4 of these clamps per punching machine. This clamp allows the sheet metals to actually be moved along the workstation. Currently, they're being cut from hot rolled metal block, then CNC machined with about a 2+ week lead time, costing them about $300 US, about 280 euros. They're able to now they're able to move to printing this component, and you can see the sheet metal clamp here on screen, able to redesign it, and then they're able to 3D print that part. You can see the original component as well as the printed component up above, very, very similar in design. But now we're getting a much, much simpler manufacturing process because we're able to simply print the part. You can see one of the topology optimized parts here as well, where they're looking to further reduce the mass of this component by incorporating some of these lightweighting features. Another part here is this spring holder hanger. This is part of a paneling machine. The components actually coupled with a gear that allows the arm to rotate. Generally, it takes them 7 days to receive the part if it's in stock. If not, it's even longer because it's going to require it to be custom machined. Currently, that part's costing them about $65 US. So they're looking to lower the costs. They also had some issues with some tear out. You can see the tear out on this part. The part wasn't strong enough, so they needed to move to increase the strength. So they really saw 4 key benefits here using metal 3D printing. Stronger. They're now free to modify the design for an increased strength. You can see some of the ribs they're able to add. They're able to increase the thickness. Faster. They're able to manufacture in just 4 days. They were able to manufacture 6 different samples ready to be mounted in the machine without any post-processing involved. Cheaper. The part cost was about 75% less, 15 euros versus 60 euros, and then less waste. They're able to reduce material waste relative to CNC machining because, of course, this is an additive process. The 4 key benefits, with this sheet metal clamp that we talked about earlier, lighter with infill alone, they're able to reduce the mass by about 17%. Faster, about 2 times faster, 7 days versus 2+ weeks. Cheaper, about 36% lower cost, 176 versus 279, and then much less waste, of course, because it's an additive process. So big business impact here. The ability to print replacement parts for the manufacturing floor. They're able to lower their costs, minimizing CNC machining labor and lead times. They're able to improve equipment reliability due to this mass reduction, and then design freedom, of course. They have the freedom to design whatever they need, increase strength, reduce weight, really giving them some freedom with their design. That's all I have for you here today. Next step, I'd love to explore, what additive can do for your business. I'd love to set up a one-on-one meeting with you to talk through additive manufacturing. You're going to get a follow-up email to this with some slides as well as the recording. We'd love to know, what you're doing with your business, what applications you have, to see really where 3D printing could be a good fit for you. I'm happy to give you a free part assessment with some part metrics. If you want to send me a CAD file, I'm happy to review that part, let you know if I think it would be a good part for the process, how much it would cost, how long it would take, etc. Thanks again, everyone. We're going to be doing a lot of these webinars, so head over to desktopmetal.com/connect/events, where you're going to be able to sign up for tons of these webinars. If you want to learn more about Studio System or the Shop System or the Fiber System, we're going to do some deep dive webinars on those. And of course, feel free to email me at any time, ethan@desktopmetal.com. I'm happy to take any questions, thoughts, comments. Always happy to talk about 3D printing. All right, thanks everyone. Have a good day. I hope everyone is staying safe.